Let us go back to what we wanted with the amplifier. Maybe you remember we had three important characteristics: the input impedance, the output impedance of the amplifier, and the transfer characteristics. And let's say we have an amplifier that has certain input and transfer and output characteristics, and that we are using another technique to make the source to load transfer independent of those input and output characteristics. So let's say here we want to have a voltage amplifier. We have here a voltage source Vs with a source impedance, and we have a load impedance and a voltage across it. So we want to have an accurate and stable voltage transfer from Vs to V load. But we have an amplifier that has a finite non-zero input impedance and a finite non-zero output impedance. And both the source impedance and the input and the output impedance of the amplifier and the load impedance, they all can be, for example, nonlinear. That means signal dependent or inaccurately known. And we want to make an accurate transfer from Vs to Vl. What do we need to do then? Because we have basically then a transfer from the source to the input, which is inaccurate, and also from the load, which is inaccurate and maybe signal dependent. And as you know, as soon as we add something that is not fully predictable, we add noise. So also this can be regarded as a limitation of the information handling capability of the amplifier. So here we have the transfer of the amplifier. VL or Vs can be written in three parts: the transfer from the Vs to Vi, the first part; the second part, the voltage gain that is included in the amplifier from Vi to Vo, which is the strength of the controlled source; and then the transfer from Vo to VL, which is the last part. And we focus on the fact that the first part and the last part are not accurately known and maybe even signal dependent. So a brute force technique would then say, well, put something in series, for example, with the source impedance or the input impedance, and in parallel with the load impedance, so that we have a very high input impedance, making the transfer independent of the source and the input impedance, and we create a very low output impedance and improving the accuracy of the last term. So we could do it as such, as described here: put an impedance in series with the signal path and put a impedance in parallel with the signal. Now, I hope you remember the previous presentation that we did, and we studied then the influence on impedances in parallel and series with the signal path on the noise performance. And we have concluded by then that the insertion of such impedances should be avoided because they increase the effect, the contribution of equivalent noise sources of the amplifier, and maybe they even contribute noise themselves. And at the output, there can be extra dissipation in the parallel impedance, or the dissipation in the output impedance of the amplifier increases, which makes it also less efficient. So although you could say from the expression that if the series impedance is much larger than the source impedance and the parallel impedance is much lower than the load impedance, both the source impedance and the load impedance drop from the equation. So it is more accurate. We don't have any inaccuracy left from the source and the load impedance, but we may have deteriorated noise performance and power efficiency. So remember, this is the rule: no impedances in series or in parallel with the signal path. At the source, they gave a reduction of the signal to noise ratio, and at the load, they decrease the power efficiency. And of course, the source to load transfer has an attenuation if you do so. What we also have seen then, if we use this brute force method, there's a strong interaction between accuracy and noise addition, accuracy and power inefficiency, and accuracy and the source to load transfer, which really doesn't sound very like orthogonal design to me. We need a better technique than this.